Okay. So before I will introduce Professor Arun ROSS. So Professor Arun ROSS is a professor at the Department of Computer Science Engineering at Michigan State University. He's the director of the Integrated Pattern Recognition Biometrics Lab. He also serves as the seat director of the NSF Center for Identification Technology Research. Arun ROSS conducts research on the topic of biometrics, privacy, computer vision, and pattern recognition. He is recipient of many prizes, among Agarwal, Young Biometric Investigator Award, NSF Career Award, and so on. So, I mean, if I want to resume a little bit, Professor Arun ROSS is one of the top researchers in biometrics, and we are very proud to welcome him and to let him this keynote for this last session of the conference. So please, we are here for you.
Thank you very much, Christophe, for the kind introduction. I hope you can hear me, just to confirm, and then I'll start my presentation.
Yeah, perfectly. Thank you.
Wonderful. Thank you. So this presentation is titled Biometrics Under Attack, and it has several different connotations that hopefully we can traverse during the course of this, this keynote. Once again, thank you for inviting me, and I can see that this is a very interesting conference. I enjoyed the previous talk as well, and hopefully moving forward we can have more interactions. Just to set the ball rolling, I'm from the iProbe lab at Michigan State University, working with a number of PhD students and postdoc and undergraduate students. And of course, now we're all working from home, which I believe is the situation in many parts of the world right now. But hopefully when the situation changes, I look forward to seeing some of you in person, and perhaps some of you can also travel at that point in time to Michigan State University. The research theme of our lab is kind of summarized here with respect to biometrics. We also do some work in autonomous driving and medical imaging, and also plant phenomics. But in the context of biometrics, really we have three distinct themes. One is on the topic of adversarial biometrics, where you could think of problems like spoofing biometric traits, or altered biometric data, or even degraded biometric data that can cause the biometric system to fail, or even for an adversary to circumvent the normal operating perspective of a biometric system. And then there is the issue of privacy, especially because we're talking about biometric data, and I haven't really defined what biometrics is, but I'm sure that all of you know what biometrics is, although formally I will present a few slides just to ensure that we're all on the same page. But the question about what else is revealed in a person's biometric data is a very important question. And how can we enhance the privacy of biometrics that is increasingly taking on some very important overtones in the biometrics community, especially in the wake of well thought out regulations such as GDPR. And then there is this aspect of fusion, because biometric systems are prone to failures. And so how can you enhance the performance of a biometric system? And how can you integrate that biometric system with the application? And this leads to a lot of questions in a field called fusion, be it when you're combining multiple different biometric cues, or you're combining a biometric module with, say, a spoof detection module, which is trying to determine if the data that is being presented to the sensor is legitimate data, or if it is an adversary who's presenting some fake biometric traits. Our project is funded by a number of organizations, and we are grateful to these organizations for their support over the past several years. So as I promised, let me just provide a working definition of biometrics, although given the theme of this particular conference, I'm sure all of you are familiar with the terminology here. But biometrics is the automated recognition of individuals based on their biological and behavioral characteristics. So if you look at that first bullet point, there are several keywords that are highlighted. One is it is the recognition of individuals. And so what biometrics does is it connects two biometric samples and then determines if they originate from the same source or not, hence the connotation of recognition. And then you have this notion of biological and behavioral characteristics. So it pertains to an individual, and you're looking at characteristics that are perhaps innate to an individual. But equally important is the second bullet point in this slide, which tells us that these traits, these biometric characteristics, have to possess at least two ideal properties. One is that they have to be distinguishing. Sometimes that is referred to as the uniqueness aspect of a biometric trait, how unique it is to an individual, or even how distinctive it is, and therefore how does it distinguish and disambiguate between individuals. So that is the notion of uniqueness. And then it says repeatable features, and this is again the notion of permanence, where one would expect the biometric trait to have some degree of stability so that data collected after a time lapse is still successfully matched with the original data of the same person. And on the right of this view graph, you see what is called as a Berthian card from the late 19th century. Alphonse Berthian raised a very important question, which is how do we recognize individuals in a very systematic manner? What kind of science goes behind it? And so he came up with a strategy where a human operator, because we're talking about the late 19th century here, where a human operator would measure certain geometric attributes of an individual, such as the length of the hand, the height of the individual, the length of the index finger, and so on and so forth, and meticulously record this in a card, which came to be known as Berthian card. And these features were then used to compare the attributes of an individual with the card. And then if there was a match, then of course they would conclude that these two individuals are the same. So again, biometrics has come a long way, and it is now an automated technology. And in some applications, it is semi-automated, where a human operator might also be involved. So there are a vast array of biometric traits, some of which have been studied more than others. You have fingerprints, palm prints, iris, voice, signature, all in the first row of this particular view graph. And then if you come down to the middle row, you see face, DNA, conjunctival vasculature. These are blood vessel patterns that are visible through the white of the eye. And sometimes you can also get scleral patterns, the texture that is resident on the sclera of the eye. And these can be used also for recognition purposes. And then you have ear biometrics, you have keyboard typing patterns, dental biometrics, gait biometrics, hand geometry, vasculature patterns in the back of the hand, and ECG. So the list goes on. And clearly, as I said earlier, some biometric traits are more extensively studied than others. And in particular, the question that was posed in the last slide, how unique is a biometric trait to an individual and how stable or permanent it is, are two pivotal questions in the consideration of a biometric trait. And at this point in time, not all biometric traits have been reliably evaluated with respect to these two very simple tenets of biometrics, uniqueness and permanence. And therefore, there is a fascinating research problem and a very good PhD topic for one to work on, even for some of the more popular biometric traits such as fingerprints. So what is biometric comparison? Just for completeness sake, here is an example. You have two face image, or rather two face images. And really you would like to estimate two numbers. One is the likelihood that assuming they are of the same person. What do I mean by that? the likelihood of observing these two face images under the assumption they are of the same person. So we call this as the probability function. In this case, it's a density function, the probability density function of what is known as the genuine class. So under the hypothesis that they are of the same person, and then you have the alternate hypothesis, which is the likelihood of observing these two face images under the hypothesis that they are of different people, because you should allow for the second hypothesis to also exist. And so ideally, you would compute what is called as a likelihood ratio between the two bullet points, one being the numerator and the other being the denominator. And then if that likelihood ratio, if it would exceed a certain threshold, then you would conclude that these two individuals belong, or rather these two face images belong to the same individual. Now, not all biometric systems approach the problem in this fashion. And this is where I'd like to take a pause and kind of reflect on this, which is most biometric systems would say that if these two images look similar, according to some set of features, then they belong to the same individual. So they would use a similarity measure in order to make the conclusion as to whether these two images belong to the same individual or not. But the challenge in using the similarity measure is that it can be misleading. Just because two objects look alike do not necessarily mean, or if two images look alike, it doesn't necessarily mean they come from the same object. But this is where there is a tremendous discussion and collaboration between biometrics and forensics, because in the case of forensics, one often wishes to answer the denominator. Given these two images, what is the likelihood under the assumption that they are of different people? So these are fascinating questions, and as many things in computer vision, often similarity is used to suggest that they originate from the same source, but one also has to look at features that are different, which might lend to the hypothesis that they indeed are of different people. And of course, that question is not confined to face images. It is true for fingerprints, it's true for iris, it is true for hand geometry, and so on and so forth. Again, just in the interest of summarizing a biometric system, you have a sensor which acquires the biometric data, a feature extractor which extracts a set of discriminative features from the image, and then one needs a comparator to compare two extracted feature sets. And in many cases, some of these feature sets during enrollment are stored in a database, or what we call as a gallery. And these templates, as we call them, or reference data of individuals are stored in a database along with an identifier so that they can be used for biometric recognition purposes. And so we have two terms. A probe is the data that is offered to the system, which has to be recognized, and the gallery is the set of labeled data that facilitates the recognition process. And so you have these modules, but increasingly, because of the use of deep learning, the feature extractor and the comparator modules have been brought together. Previously, one had to handcraft features. If you take fingerprints, for example, then from the branch of forensics, people were looking at minutia points. These are ridge anomalies, and a constellation of these minutia points was believed to be unique to an individual. And so biometric systems also started using minutia points. And so in that case, the feature extractor would be designed in such a way that it could extract these seemingly discriminate features. And then a comparison algorithm would be implemented. But increasingly, because of the use of deep learning methods, the features that have to be extracted are often defined by the machine itself, because the machine learns what kind of features to extract. And this would lead to several problems. One problem would be that the interpretability of these features is lost, which can be very important in applications such as a code of law under Daubert's criteria, of course, but it would be difficult to explain what kind of features the machine is extracting. And so therefore now there is a tremendous focus on what is called as explainable AI or explainable deep learning, in which researchers are attempting to equip these networks with the ability to visualize what kind of features are being extracted. At the same time, deep networks have resulted clearly a massive change in the landscape of biometrics, as I will say in a couple of slides downstream. A number of applications ranging from healthcare to banking to personalization to border security to services. There is a vast number of biometric applications, and clearly the purview of biometrics is likely to increase over the next several years, especially due to the explosion of Internet of Things, where now you not only have to evaluate a device that is a part of this massive network, but you also have to authenticate the user or the subject who's using that device, both for security purposes as well as personalization purposes. And so clearly the scope of biometrics is expanding, and the need for reliable establishment of identity is a very critical problem now in society, which is interconnected. So moving on to the real world, the similarity between two instances of biometric data can be corrupted by noise. And here you see some examples. On the upper left, you see two fingerprints, and the image on the left there clearly has much inferior quality because it was lifted from a crime scene, whereas the image on the right is of much better quality because it was obtained in a very cooperative manner. And similarly, if you look at the lower right image, you see two sub-images, with the left sub-image being of potentially being of higher quality, at least visually, than the right sub-image. And this can lead to data being corrupted, which can potentially lead to what we call as a false non-match, especially when these two images belong to the same individual. And if the system were to say that it can't match these two, then one would say that this is a false non-match. Or it could also result in a false match because of the corruption in the data. It can inadvertently match with the incorrect subject. And so we understand that data that is corrupted by noise can lead to some unintended consequences. On one hand, it could be a false non-match, and on the other hand, it can be a false match, both of which may not be acceptable. The other problems here, as we think about the challenges facing a biometric system, and we have used face as an example, is intra-user variations, which can lead to a false non-match rate because the same user looks different in different scenarios, and that can lead to a large intra-class variation and finally result in a false non-match. The opposite problem would be inter-user similarity or inter-class similarity in the case of doppelgangers or twins or siblings or parent-child situation, where there can be individuals who look alike. And this can result in a false match rate because of the similarity between individuals. And this kind of highlights the earlier point I made, that if one were to use purely the degree of similarity or dissimilarity in order to come up with a match score, which is then used to say if the two images are of the same individual or not, then this would be problematic. And hence the need to look at both types of hypothesis, pertaining to if they are of the same person and if they are not of the same person. But clearly, that denominator that I talked about in the likelihood ratio is very difficult to estimate, not because of anything mathematical, but purely because of the lack of data to reliably estimate that denominator in the context of the likelihood ratio. Other problems persist, noisy data, which can, as I said, impact both false match rate and false non-match rate. And in case you're wondering, why am I just talking about the challenges in a biometric system? Well, the short answer is that it represents a tremendous opportunity for researchers to work in this field. And if the right problem is selected, it can have a tremendous impact in the field. Many people might even consider biometrics to be a solved problem. It's not. It's far from it. There are problems ranging from noisy data to privacy, and then to security when these systems are installed in large-scale applications. And so clearly, there is a vast array of problems that the community has to solve, and therefore, in that sense, it represents a very rich area of research. And then, of course, the problem of biometric aging. You're talking about biology and biological tissues age, but how can you still extract invariant features, features that are stable over a person's lifetime? And that's not an easy question to answer. One, there is a lack of data, and two, equipping mathematical models with biological underpinnings is often not the easiest thing to do. And so therefore there is a need for having these models that are biologically informed, not necessarily just statistically sound, but it has to be informed by the biology of the biometric trait. And clearly biometric aging can impact what we call as the false non-match rate, because it can lead to an increase in the false non-match rate. So if we think about the state of the art, notwithstanding all the problems that were highlighted in the previous slides, and if you look at the National Institute of Standards and Technology, NIST in the United States, that has been conducting face evaluations for a long time, we notice that the convolutional neural network-based techniques have changed the landscape. So here is one example amongst the many kinds of evaluations that have been conducted by NIST. They had a gallery size of 1.6 million identities. You're talking about face recognition. And in 2018, the best algorithm gave a false negative identification rate of 0.2% on this database. And in 2014, the best performing algorithm had an error rate, false negative identification rate of 4.1% at a very low false positive identification rate. So here we notice that there has been a 20-fold reduction in false negatives, which is a good thing, just over a period of 4 years. And as the report points out, the massive accuracy gains are consistent with an industrial revolution associated with the incorporation of neural network-based techniques into the prototypes. And so here we see how much CNNs have changed the landscape in the case of face recognition. But at the same time, one must concede that many of these CNNs are not easily interpretable. And like I said earlier, there is an increasing onus on developing techniques that are interpretable and explainable. But even if they're not explainable and even if they're not interpretable, on the other hand, you see that the performance numbers are compelling. And so hopefully people will begin to connect the dots between performance on one hand and explainability on the other hand, because that would lead credence to the technology. And so if you start looking at other modalities, even something like iris, those numbers are very competitive. And here, a one-to-many matcher, what is referred to as an identification scenario, yields a false negative identification rate of 0.67%, 0.67% at a very low false positive identification rate. And so similarly for a one-to-one matcher, what we call as a verification scenario, the false non-match rate is 0.57%. And so clearly we see here that these numbers are very competitive when it comes to biometrics, but there is also a caveat to this. And often the caveat has to do with the quality of the data that is being used for the evaluations. And in many cases, when one uses operational data in unconstrained scenarios, what we call as in the wild images, for example, surveillance images, these numbers can be impacted, not just for iris, because iris, the data is often acquired at close quarters, but in the case of face also, the performance numbers can be perturbed when one deals with situations that are unconstrained. So as we move forward, we now think about an adversary who's attacking a biometric system. So this is not errors that happen by chance. These are errors within quotes that are designed to occur because there is an active adversary who's trying to undermine the working of a system. And so one example is spoofing, where one is either altering a trait or creating a physical artifact in order to spoof, for example, another person's trait. And so you see here the application of makeup. You see here a replay attack where the image of a person is displayed on a screen and then presented to a smartphone or vice versa. And then you have here methods to create fake fingerprints, or even have printed iris images or artificial eyes that can potentially be used to confound a biometric system. And we have shown that the strategic application of makeup can be problematic. Just by taking images from YouTube, we were able to demonstrate that individuals who apply makeup in order to match a target identity, in some cases can be successful. So here you have 3 images. On the left, you have an image before makeup, and then in the middle, you have the subject applying makeup, and their goal was to mimic the identity of the person on the extreme right. And so before the application of makeup, the target identity was matched at rank 734 out of about 13,000 identities. But then the application of makeup moved it to rank 1. And so clearly, cosmetics can be applied strategically in order to either obfuscate, as we will see in the next slide, or to spoof someone else's identity. Well, we talked about obfuscation, which is defined as masking one's own identity by altering the trait, and makeup can be used in many cases to obfuscate someone's identity, and in many cases it can be inadvertently done. These are socially acceptable changes, so not necessarily adversarial in that sense, but it's adversarial with respect to the system, because now the system has to contend with the same individual looking dramatically different under different scenarios. So these examples are representative of some of the adversarial attacks, and I put attacks within quotes, but these are adversarial attacks that can be launched against a biometric system. And there are new challenges to face recognition, as we all go through this pandemic, we realize the importance of using masks, and this again adds a new dimension to face recognition. Now, how do you match these partial face images with the full face images that are in the database? And so there is much work going on in periocular biometrics, where just the region surrounding the eye is used to recognize an individual, and there can be a performance drop. But on the other hand, people are looking at cues even in the ocular region that can better denote an individual in scenarios that I just alluded to. There can be other adversarial attacks against a biometric system, fingerprint alteration, where a person can deliberately mutilate their fingerprint, as was the case in 1995. And there are many other examples where a man named Alexander Guzman was arrested by Florida officials for possessing a false passport. but then they found that he had mutilated fingerprints, so they had to manually reconstruct the damaged fingerprints, well, really digitally reconstruct the damaged fingerprints, and then they searched the FBI database and then linked him to an absconding drug criminal. And the attack that he had undertaken really mutilated his fingerprints was an attack called as a Z-shaped cut, whereas you can see here on the left is the original fingerprint, and on the right you see the modified fingerprint, where the Z cut was employed in order to transplant and surgically switch two triangles, and this led to the image not matching with the identity in the database, and hence it had to be digitally reconstructed in order for the officials to find out who the individual was. So clearly, biometric systems are vulnerable to these type of attacks. How do you determine if an image that is presented to the system is a legitimate image, or if it has been altered using surgical procedures or through the application of makeup, or if it is just a fake biometric trait that is does not pertain to any individual? So these are important questions that biometric researchers are now addressing more and more. And in the remainder of the time, I want to very quickly speak about some of the other types of attacks and ways to mitigate them. And one attack is the master print attack. And the master print attack comes about because of the use of small fingerprint sensors like the ones that you will see in many a smartphone. Because these are small sensors, they only capture a small portion of the fingerprint that is indicated using these squares, the red, yellow, blue, and green squares. Rather than the full fingerprint, only a portion of the fingerprint is captured. And so the way the systems deal with this is, rather than just capturing one impression, they capture multiple partial fingerprints. And so the system might ask you to place your fingerprint multiple times and exposing different areas of your fingerprint so that it is able to get a better understanding of the full extent of your fingerprint. But the way it works is that the system, in many cases, stores multiple impressions, and you can then have multiple fingers also enrolled. And a match is said to occur if the input fingerprint matches with any one of these partial impressions. So these partial impressions are not necessarily used to construct a more elaborate fingerprint. They are just treated in some cases as independent impressions. And so an access is granted if the input fingerprint, which is also partial, matches with any one of the partial fingerprints of any enrolled finger. And so this represents a risk because you're now looking at a small region of the fingerprint as opposed to the full fingerprint. And so the chances of the small portion inadvertently matching with someone else's fingerprint increases. And this is where we coined the term master prints. It's like a master key that can open any lock in the building. And so master prints, in the similar vein, are fingerprints that can inadvertently match with a large proportion of the fingerprint population. And these could be full fingerprints or even partial fingerprints, but clearly partial fingerprints are more vulnerable to this kind of an attack. And so here are some examples of master prints that we had generated for a specific database because these images can inadvertently match with a large proportion of partial fingerprints pertaining to multiple identities in the database. One clarification, these are actually not images that we generated. These are images that we cropped out from the database, which would still match a large proportion of fingerprints. So clearly we notice here both the vulnerability of small fingerprint sensors, but more importantly, the existence of these master prints that can compromise the identity of many individuals. And so here are 10 different subjects. This is, if you look at the small fingerprints at the bottom part of the screen, each row corresponds to one subject. And you can see here that there are 12 fingerprint impressions for every subject. This is from the FingerPass data set. And on the top, you see here some master fingerprints. And so you notice here that these master fingerprints, they coincidentally, fortuitously match with a subset of impressions belonging to the same individual. And you can see that, there are 1, 2, 3, 4, 5, 6, 7, 8 check marks here, indicating that 8 out of the 10 subjects were inadvertently matched with these master prints, which means if you have one of these master prints, you can potentially unlock many different smartphones. And so this represents a realistic threat. And we did some experiments to show the vulnerability of fingerprint identities, or identities based on fingerprints, to this kind of a dictionary attack. We call this as a dictionary attack because you have a dictionary of 5 or 6 master prints, which can be used in order to compromise a system. But later on, rather than using images that were cropped out from an existing database, what we did is we raised the question, can these be generated synthetically, especially with GANs, generative adversarial neural networks? Can we come up with a technique where we can actually generate master prints? And as it happened, we showed that we can generate digitally these master prints. On the upper row here, you see on the left and the right, fingerprints from a real database. And then in the lower part, you see fingerprint images that were synthesized using GANs. But these were strategically synthesized in order to match a large proportion of users. And so these are, in that sense, master prints, and we call them as deep master prints because of the use of GANs and deep networks to generate them. And what we showed was in our experiments that a single deep master print can match a large proportion of users in a database, even if the threshold is very strict, 0.1% false match rate. For example, still the single deep master print could match 22.5% of the identities in the test data set, which is different from the training data set. And so clearly, this is a very realistic attack, especially if these master prints are converted to a physical artifact that someone can carry with them. And so that would be a vulnerability. And then we came up with techniques to attack, or rather to resist this attack. And one of the things that we developed is an algorithm that does not indiscriminately use all the partial fingerprint impressions that you provide during enrollment. What it does is it goes over the images that you provide during enrollment and selects an optimal number of templates in such a way that the attack can be deflected. And so much of it is discussed in our 2019 paper titled Master Print Attack Resistance, on how template selection, on how image selection can be done strategically in order to rebuff the attack from the use of master prints. We did some experiments to show that the proposed technique can reduce the attack accuracy by 12%, and so it has tremendous benefits if it is implemented. The other kind of attack has to do with modifying digital images. And in this case, for example, you have near duplicates of the same person. They are subtly modified images. And they can be done adversarially because someone might deliberately modify an image so that it does not match with another image. And that can prove to be a ploy in a court of law, where someone might deliberately try to modify an image and thereby minimizing its chances of matching with the correct identity. The other issue could be an image could be strategically modified. And by that I mean it may not be visually discernible, but it can be modified ever so slightly so that it matches with someone else. And one could imagine the implications and ramifications if that were to occur in a court of law kind of application. And all of us are familiar with deep fakes. These are synthetically generated images which look very realistic And I'm sure that all of you have used this website, thispersondoesnotexist.com, where the GANs are used to generate synthetic images. And presumably none of these images would match with anyone in the world, although that has not been demonstrated. These are synthetic images, not necessarily pertaining to a known individual. And this also represents a challenge. In some cases, there are some artifacts in the image that can suggest to us that this is perhaps a deep fake, but it's not a very simple problem. Although there are some algorithms out there that can detect deep fakes, they are often not generalizable. And as GANs become more and more powerful, and as people become more and more innovative, it becomes a cat and mouse game. How can you detect these deep fakes? Because deep fake can be used to create virtual identities, and that can have some problems, especially in security applications. Another well-known problem in the community is creating morphed faces. And so if you look at the left set of images here, here are two individuals labeled as ID1 and ID2, and one can morph these two images to create this middle image. Hope my pointer can be seen. That is the morphed image. And researchers have shown that this morphed image can match with two identities now. And the original paper from David Maltoni's group is titled The Magic Passport, because now you can have a passport that can be shared potentially between two identities. And if this is done in an adversarial manner, then you have an adversary or two adversaries here who are trying to use the same passport, and normally that is not a very good thing, as you would imagine. And so clearly here, when we talk about digital data, there are ways in which this data itself can be modified, and in this case, creating morphs can undermine the utility of a biometric system. And so the notion of image forensics has become very important now in biometrics. Questions like, which sensor produced this image? Is this an altered image? Is this a synthetic image? And if you have a set of images, you ask the question, how are these images related? And so these are important questions that are now being asked even before you process the data, ranging from which sensor produced this image, and is this an altered or synthetic image, or how are these images related if you have a set of images? What kind of transformations were applied in order to transform it from one image to the other, and were these transformations done with the intention of circumventing the system? So these are very important questions that are now being raised in the context of biometrics. And the goal, of course, is to ensure that the biometric system is operating on valid and legitimate data. And so this question about relationship between near duplicate images is something that we are working on right now. Given a set of images labeled here as 1, 2, 3, 4, and 5, can we now create this tree? And we use the term Phylogenetry, borrowing it from genetics, but it has got nothing to do with genetics here, except to say that these images are related in this hierarchical fashion. That image number 5 is the original image, and some transformation was applied in order to get image number 2, and similarly another transformation for 3, and then from 5 to 4, and then from 4 to 1. So how can you automatically, without using any metadata or EXIF data, make these determinations? And this is an important problem. And we have tried to both motivate the importance of this problem and also provided some preliminary solutions in order to address this problem. Clearly, this is an important problem because it can be used to detect image tampering, or even to find out if images are related to each other. I won't go into the details except to say that we have a two-step process to construct what is called as the IPT. I refer to that as image phylogenetry. That's what IPT is, where you take a set of images denoted as nodes. You generate what we call as an asymmetric similarity matrix, and from this matrix we derive this kind of a tree an acyclic tree that is used to denote the relationship between the participating images. So clearly the challenges are many. We don't know what kind of transformations are being applied, because with Photoshop and many such software, there are potentially infinite number of transformations that can be applied to an image. And so the way we approached it very briefly is to model the relationship between two images using a parametric function, and then using the likelihood of the parameters to determine the relationship between the two images. I'm not going to go into too much detail, except to say that if you have two images, B and A, what we try to do is we use a parametric function to help understand how A is transformed to B via this transformation function. And in our 2019 paper and in our more recent 2020 paper in the T-biome transactions, we show that this particular transformation function can be denoted using some basis functions. And so we explored various basis functions from Legendre polynomials to Gaussian functions. And then the parameters that were estimated were put in a likelihood ratio framework in order to determine the relationship between images. A large set of experiments were conducted. And what we showed was you could identify the root node. That means what is the original image, with an accuracy of about 81%. And you can actually reconstruct the whole tree like this, showing the relationship between the various images with an accuracy of about 67% or 66%. And this might seem to be low in number, but one must consider that the previous state of the art would give you 18.75%. And so clearly there is a benefit in modeling the relationship between near duplicate images using these polynomials and other kinds of radial basis functions. So the final set of slides has to do with privacy, because we're running out of time. So I just want to briefly talk about privacy. Privacy is also a very important aspect of biometrics, because now in many places, people are beginning to ban the use of face recognition. And amongst other reasons, there is a great concern about privacy. One connotation of privacy can be described in this slide. I give a face image, and you actually can automatically deduce various attributes of this individual. And so even though this is a biometric image, you don't need a matching image in order to deduce some attributes of this individual. Just using a single image, and by relying on a trained classifier or a regressor, you can extract some information about an individual. And you can do that even with modalities such as iris, because with respect to face, it seems to be intuitive. But in the case of iris, it is not that very straightforward. But what we have demonstrated is that if you were to give a single iris image, which also exposes the ocular region, you can potentially extract information about a person's gender, about a person's race, and in some cases, which camera was used to produce the system, and also a semantic commentary about the image. For example, that this is an image which has a highly constricted pupil, and therefore this could suggest that there was a strong ambient illumination. So clearly here, the single image that was presumably collected for biometric recognition purposes is now being used in order to deduce other attributes of an individual, and this can clearly violate the privacy of an individual. So on one hand, you could say, well, this bridges the gap between human and machine descriptions of data. On the other hand, one could legitimately claim that this can compromise the privacy. So in order to deal with this problem, we have come up with some solutions. But before that, here is another example where face images are being used in order to deduce the existence of certain genetic disorders in an individual. And this application called Face to Gene, which is available to many medical providers, can potentially be used for this purpose, where the face image is mapped to some gene syndromes, and therefore it can be used to detect genetic disorders. So one raises the question, can we have control over this data that we are providing to, say, a vendor? And so ideally, we want to be able to take an image and use it for recognition purposes, but we don't want to use it for extracting these other attributes such as gender, age, race, health cues, etc. So you want to retain some functionality and want to confound other kinds of functionality. And so we have this concept of semi-adversarial networks that we have developed. What this does is it takes an input image and modifies it, creates an output image. This output image can be used for recognition purposes. That means the face matcher is operational. But say a gender classifier is confounded. And so we call it semi-adversarial because it is adversarial with respect to one class of classifiers, and it's not adversarial with another class of classifiers. Just taking a sip of water here. And then here is the architecture of the semi-adversarial network model. You have it's a convolutional autoencoder really, but during training, there are two auxiliary matchers or classifiers. One is a face classifier and the other is a gender classifier. And what these two auxiliary units do is that they guide the loss function of this autoencoder in such a way that the output image can be used by a face matcher successfully, but cannot be used by a gender classifier. Clearly, one must also notice here that anytime you try to impart security and privacy, you might observe an attendant drop in matching performance. And that clearly is the biggest challenge, and it is no different here. And that's the part where what we're trying to do is to minimize the loss in matching accuracy even after the image is perturbed and it is not usable for other purposes. And so the example here, you have an input image, which is labeled as a female middle-aged Caucasian. And can we now modify this image in such a way that the classifier, not the human eye, the classifier, and hence the term automated, the classifier is confounded. And so here, for example, the target label has to be female old Caucasian or female middle-aged non-Caucasian, and so on and so forth. So these are some of the things we're doing, keeping in mind the sensitivity of using these terminologies, the notion of gender, the notion of race, the notion of age. These are terms that have to be very cautiously used. They have specific connotations, and sometimes even in the biometrics literature, they're very loosely used, and that can cause confusion. But one has to be very careful when these terms are being used, especially when it is used in the context of modifying an image. What does it mean? And so these are very important considerations that we have to take into account. But nevertheless, what this technique does is it basically takes an input image and modifies it in such a way that some attributes can be extracted, whereas other attributes cannot be successfully extracted. We call this as the privacy net. And it's a recent paper of ours, which is in the press, in the Transactions of Image Processing, which talks about this network, this neural network that can be used to do this. So let me just stop here to say that there is a tension in biometric solutions. You want biometric solutions that can satisfy diverse criteria, from effective data acquisition to robust matching algorithms, to provable security and privacy under diverse conditions over large heterogeneous populations. A very challenging task for biometrics. And that's why, as I said earlier, it is a very rich area of research. And I'd welcome you to conduct research in this area because it is a technology that can impact society in the days to come. Christophe, I'll stop there. And I apologize, I think I took more time than I should have. But I appreciate the opportunity, and if there is time for questions, I'll be very happy to field some questions.